We learned a very important concept in the last video, fundamental set of solutions. So what is it? So we learned it through a jigsaw puzzle example, right? I'm going to say it again because it's very important concept. Now let's say you are given a jigsaw puzzle that you need to finish, but you are given lots of pieces, let's say 1,000 pieces, okay? But in those pieces you have pieces from another different jigsaw puzzle also. Okay, so what do you want to do first? You want to know how many pieces that you need first, right? Because your jigsaw puzzle that you need to finish might only need 100, so you need 100 pieces. Then the next thing is you want to make sure you get the pieces that belongs to the jigsaw puzzle that you want to finish, not the pieces of something else, so you get that correct pieces. Third, you want to find whether these pieces are different pieces, because someone might have photocopied those pieces or made exactly copies of the same pieces. So you want to remove those copies and get those distinct pieces that will fit into the whole jigsaw puzzle. So that's the idea of solving a homogeneous nth order differential equation. So you take this differential equation, you look at the order. So n is the order, could be second order, third order, fourth order, something like that. Now you need n number of solution pieces, right? So second order differential equation need 2 pieces, third order differential equation need 3 pieces. So you get the correct number of pieces. Then you make sure these are like the solutions of the differential equation. They could be some random function, okay? So you want to make sure that they are the solution, so you verify it. Third, what you do is you want to make sure that they are not copies of each other, they are not linearly dependent, so you find those linearly independent solutions, okay? So likewise we call that set a fundamental set of solutions. So let's say you have an nth order differential equation, and let's say the fundamental set of solution is from y1 to yn. Okay, now why do we need this fundamental set? Because now you have n number of solutions, but how do you produce one solution out of it? What you do is you take the linear combination. We learn through the superposition principle that the linear combination, okay, is also a solution for the differential equation. So this is also a solution. These are also solutions, but this big one is also a solution. So instead of writing this as this big list, we write this general representation of those all solutions in that collection. The collection means the fundamental set. So this is the general solution for a homogeneous differential equation. Okay. All right. Now I am going to give it a new name. A solution for a homogeneous differential equation, the general solution, is called the complementary function. Okay, so we denote it by y sub c. So this is not y, it's now we say y sub c. Okay, c stands for complementary. So a solution for a differential equation is again said a complementary function. Okay, all right. Now why are we learning this again? Because now we want to solve non-homogeneous differential equations. That means now in your differential equation on the right hand side, simply you have gx, a non-zero function. Here's the tricky part. Now understand this. What I'm going to say is that to solve a non-homogeneous differential equation, you have to solve a homogeneous differential equation. Wait a minute, what are you saying, right? Here's what happens. Let's say you are given a non-homogeneous differential equation. The very first thing you do is, okay, I have that g, that is why this equation is non-homogeneous. So now what I'm going to do is I'm going to pretend, or I'm going to assume I don't have g. I'm going to assume that I have 0 here. Now what you do is simply like you remove that g and you replace it by c, then you get a homogeneous differential equation, right? So what you do is you first solve that. Okay, so we first solve that and we find y sub c, the complementary solution of that homogeneous equation, or I should say the homogeneous version of the original non-homogeneous equation. Okay, all right. Now after you find that y sub c, what you do is you replace that g. Okay, now you look at the non-homogeneous equation. Now you don't do any pretending. Okay, you look at the original question that is given. Now what you do is you find the particular solution. So the particular solution is the solution for the non-homogeneous differential equation. So what do I mean? So that means now we take the G into account, and using that non-homogeneity, you find this specific solution which is called a particular solution. Okay, and it accounts for that non-homogeneity, so we call it y sub p. Now it might be a little bit hard to digest because we are not doing examples. Okay, we are going to do examples later in this chapter, and we learn how to solve these homogeneous and non-homogeneous equations. We will see how this yc and yp look like. Okay, so anyway, so we find this yc and yp. Yp is the particular solution. Now what you do is you present the final solution of a non-homogeneous differential equation as the summation of the complementary solution and the particular solution. Okay, so this will be a solution for the non-homogeneous differential equation. But for a homogeneous differential equation, the solution is just yc. Do you see the difference? Now that is why I said when you solve a non-homogeneous differential equation, anyway you solve a homogeneous differential equation. Okay, you have to do that in the process. Okay, do you see? So this yp is the additional part, the additional work that you're going to do when you solve a non-homogeneous differential equation. Now we call it the particular solution, and I want you to understand that that particular solution is found through that G. Okay, G here. Alright, okay, so let's see. Now a particular solution, you learn in the chapter 1, what is a particular solution? It is a solution without arbitrary constants, without parameters. So in that YP, you are not going to see C1, C2 arbitrary constants. Okay, alright, so let's look at an example. Excuse me. Here's a third order differential equation. Okay, and this is non-homogeneous. See, because 3x. Okay, now what I'm going to do is I'm going to erase that 3x and replace it by 0. So now we have a homogeneous one. This is homogeneous, this is non-homogeneous. Now what I do is I solve this one, which you will learn later how to do that. Let's see, these three are the three solutions and it form a fundamental set. So e to the 2x, e to the x and e to the 3x. We are not going to do the verification, but let's assume that they are the fundamental set. That means we can find the complementary function, right? So y sub c, we can write it as the linear combination of these three using arbitrary constant. So we find y sub c. Now what you do is you are done with that. Now go back. Okay, I erase this, I save yc. Now go back to the non-homogeneous equation. Look at 3x. Using 3x, we will construct a new solution. The procedure, we will learn it later. Okay, trust me. Using that 3x, let's say I found the solution y sub p. This is the particular solution. So this one here, as you can see, do you see arbitrary constants? No, right? It is independent of c's, no arbitrary constant. So that is the particular solution. And I found it through using that 3x, okay? Alright, so then the general solution, then the solution, yes, for the non-homogeneous equation can be written as this one, the complementary solution plus the particular solution. So that is what I have exactly done here. Okay, now when you look at what this means is, when you look at a solution, you can identify the complementary solution and the particular solution. You can distinguish them because the complementary solution will always have arbitrary constants. So see, this part is the complementary solution, this part is y sub p. So I just add y sub c to y sub p. Okay, do you see what I mean? Alright, so look at this differential equation. So for this differential equation, they say this is the solution. Okay, this is the solution. Now, which one is the particular solution? Which one is the complementary solution? So the complementary solution is actually c1 e to the 2x plus c2 e to the 5x, right? So this is the solution for the homogeneous version of this differential equation. That means homogeneous version means just replace that 24 e to the x by 0. So solution for this equation is this y sub phi. We just look at this and identify, because that is the solution part that have arbitrary constants. Now using 24ex, they have find the particular solution E as, what is the particular solution? 6ex, because 6ex doesn't have arbitrary constants. Okay, so we find y sub v, we find y sub p, and then we sum them to get that final solution of the non-homogeneous differential equation. Okay, so that's it. That is how you solve a non-homogeneous differential equation. It's just we want you to get used to the language in this chapter before we move on. And in the future chapters, what you're going to learn is how to find complementary solution, how to find the particular solution given through this G. Okay, all right, so I will see you in the next sections. Okay, bye bye.